Morning, Mr. Kane.
Morning, Mrs. G. How you doing?
Good, thank you.
Morning, class. How you doing?
You know, I'm wearing the same clothes for the last couple of videos, and I keep saying good morning.
And I've had the same tie on
really?
for a long time.
Flat out lying. We're just constantly recording here, so.
Yeah, okay. So today we're going to get in shape.
All right, molecular geometric shapes, huh, Mr. Kane?
And as you can see, of all these molecules around us,
Nice pictures.
we're gonna be discussing how molecules actually look in 3 dimensions. We've been doing it in two dimensions for so long.
Yep, been paper and penciling it a long time.
Yeah, but in order to really truly understand how things work, we got to do it 3D.
All right.
Okay, so Lewis structures are 2D. Molecular structures actually in reality are 3D.
Okay.
And there's some more, just for fun.
This is keep repeating pattern.
Yeah.
Valence shell electron pair repulsion theory.
And we pronounce that VSEPR, right?
Yep, VSEPR.
VSEPR. All right, so valence shell electron pair repulsion. Is that important to know?
Yeah.
If you're going to understand,
helps.
Yeah, if you understand the theory, you know what those you know what those words mean. All right, basically it states that electron pairs repel each other.
Correct.
Right, valence shell electron pairs repulsion.
Right.
They repel. It basically states also that lone pairs repel more than bonded pairs.
So lone pairs on the central atom require more room than bonded, and they smoosh bonded.
Mm-hmm.
Oh, we don't do bonding. Okay.
Not so much.
Not so much. But they have to know that it mushes because...
It's listed on a handout that we can give them.
Right.
But
well, they still have to know because when you have a linear, what you think is a linear, but there's a lone pair, turns to linear. Okay.
Yeah, so you have to know the concept. Yeah.
You have to know the idea. Okay.
Yeah. Yeah.
Okay.
All right, so how is VSEPR theory applied? Well, we use the Lewis structures to determine the shape of the molecule, along with the VSEPR theory, right?
Okay, so these are compounds.
It requires a 5-letter word. Think. Perfect.
So you can't predict the geometric shape of the molecule unless you know the right Lewis structure.
Correct. You got to do the Lewis structure first, which is why we've been doing Lewis structures for a couple days.
Lewis structure was done first. Okay.
So there's 2 models of the drawing. One kind is called the ball and stick model, and the other kind is called I call it the wedges and the hashes. I think the official name is the AXE method, but
all right. So there are 5 shapes that they have to know, right?
Right.
Linear, bent, trigonal planar, trigonal pyramidal or pyramid, and tetrahedral.
That's all 5 of them that we have to know. All right, so here is the first one, and yes, you do have to know what linear means.
Okay.
All right, linear means straight line. All atoms are going to line up in one plane, and they're in a straight line. So examples include hydrogen gas, which could be represented by this first structure here, right?
So any binaries are going to be linear. I mean, what do you do with a binary?
The shortest distance between 2 points is a straight line.
Yeah, straight line. The binary molecules can't have any other shape but linear.
Carbon dioxide winds up being linear. Okay,
Yep.
There's the carbon, 2 oxygens. Okay, so at any rate, they're all linear.
All right.
Okay, and notice that this is linear because it's 2 points connected by the shortest distance. This is 3 points that are in the same line. This is 2 points that are in the same line along with an electron pair that's on the outside. And this one just has 2 points, 2 atoms, and there's 2 electron pairs. We don't really look at the electron pairs when we determine shape, do we?
No, but they'll have a small part to play in shape.
They have a role to play, but
electron pairs are going to require room, so
right. But they're not going to be part of the shape.
No, electron pairs aren't part of the shape. Bent molecules. All the atoms line up in one plane, and there is usually 3 atoms. They are in the same plane, just like the picture on the bottom left, and there is usually 3 atoms to it, and not necessarily in a straight line.
No, definitely not in a straight line. Right?
Yeah, definitely not.
Because if they're in a straight line, then
it would be linear.
It'd be linear.
So it's kind of a bent molecule, and you can have either 1 lone pair or 2 lone pairs to give you a bent shape.
Yeah, but you need at least 1 lone pair, right?
Yeah,
because if you don't have 1 lone pair on that central atom, you don't have any reason to bend.
Yeah, right. Because the lone pairs are going to require more room. So they're going to bend the bonded ones down.
So this lone pair is what's causing these guys to bend down
towards each other, yeah.
And then these 2 lone pairs are what's causing these 2 guys to bend down.
Yep.
Okay. In the previous example, there was nothing causing anything to bend. These lone pairs were causing this one to bend away, but no matter which direction this one bends,
it was an equal bending.
It's an equal bending. It's linear. Trigonal planar.
All atoms line up in one plane, and then trigonal meaning 3, so there are 3 atoms, 3 legs.
And they wind up...
I beg your pardon, 4 atoms, but 3 legs.
4 atoms with 3 legs. But they wind up forming this triangle shape.
Yes.
Right? I mean, you can kind of imagine that there.
And that triangular shape is all the same plane.
Right. Notice there's no lone pairs on the central atom.
Right.
We should probably talk about the wedges and the hashes here, shouldn't we?
Yeah, how you draw it on piece of paper and pencil.
So this particular one is in the same plane as the paper, the line that we've been drawing.
Right, the straight line.
Right. This wedge that's drawn here looks to me like it's coming out of the page. Doesn't it look like,
yes,
like it's coming out of the page to you?
It's coming out towards me, yep.
Okay. And this dash looks like it's going in.
Yep, away from, like the back.
Into the page. So that's what those wedges and hashes mean.
So if you envision a piece of paper, the wedge is coming out of the paper and the hash is going behind. That's how you depict 3-dimensional things on paper.
Right.
All right.
We've got trigonal pyramidal. And not all the atoms line up in a single plane in trigonal pyramidal. Notice the same idea. It's one central atom with 3 atoms surrounding it. It's 3 terminal atoms, but we've got a pair of electrons up here. And this lone pair is causing the rest of the atoms to get bent away from it.
All right, so this is trigonal pyramidal, and this is different from trig planar because this one forms a pyramid shape, whereas trig planar forms
a flat.
Yes, basically a flat one.
Right.
Okay.
Tetrahedral, which looks a lot like that trig pyramidal, doesn't it? The ball and stick does, except for
the coloring.
The coloring. So instead of having a lone pair, tetrahedral has 4 atoms around this central atom.
Yeah.
They definitely don't all line up in a single plane.
No, gosh, no.
All right, so 4 atoms connect to the central atom. So these guys are all pushing each other away, and this angle, and the angle back here should all be the same, right?
Mm-hmm. Yeah.
And the angle up here to that guy, the angle from here to here, and the angle from here to here, those should be the same as all the rest of the angles, right?
Yep.
Because they're all pushing each other away equally.
109. Yep.
More or less. 109 degrees.
Yeah.
All right. All right. Why is this important?
Why is shape important?
It turns out that in real life applications that molecular shapes tell you about the function of molecules, how they're going to react with each other. So if you're going into the pharmaceutical industry, a lot of stuff they refer to as a lock and key. And so basically the human body's got a lot of locks in it. If you want to open it up, you have to have the right shaped key, the right shaped chemical key. Viruses do the same thing. They make keys to get into the cells. Something that's at least the picture here. It turns out that your taste buds are lock and key. Certain shapes taste a certain way. Sweet tastes a certain way. So you look for a certain shape. Turns out most of the artificial sugars look like real sugars. On the left side here, we've got a real sugar, sucrose. On the right side, we've got Splenda, which is called sucralose. There's a very slight difference in them. They're shaped almost the same. And the only real difference are these chlorine groups instead of hydroxide groups.
Yeah, different functional groups. That's a massive molecule.
It's a massive molecule, but you get the idea. It's the same shape. And the difference is that the human body can't digest this, so it can't break down sucralose, but it tastes the same because it's shaped the same.